Today we shall talk about voltmeters.
Excuse me, sir.
Yes,
Sir, I had one doubt in the last class. Uh, you
yes.
said about that switch, right? You said that the current source will give I constant, and
Yeah. So this doubt, na, these things.
yes, sir, I too
So
able to.
yeah, can we talk about it towards the end of the class?
Okay, sir.
Yeah.
Okay, sir.
Okay. So what we have seen uh, that PMMC, electrodynamic or MI, these instruments by default measure current. Their response, their deflection depends on the current flowing through the coils. Only electrostatic instrument respond directly to voltage. However, as I was saying, electrostatic instruments are not used much. They are used only for mainly for high voltage measurements. Achha. But we can use PMMC, electrodynamic, MI, these instruments also for measuring voltage using Ohm's law. Okay, so suppose I have a circuit which has two terminals that is under consideration, and I want to measure the voltage between these two terminals. Now, if I connect a PMMC or MI or electrodynamic instrument, then the current that will flow through this instrument that depends on this voltage divided by the resistance of the meter. So this current I is V by meter resistance, and I we can measure by looking at the deflection, and if I know the meter resistance, then I can measure voltage. So this is using Ohm's law. Now suppose I have a circuit and two terminals which are of importance are like this, A and B, and the voltage between AB is say V. Now the moment now if we want to measure V, so we want to measure V, this voltage. But what we will do for that? For that we will connect here a meter, and we will watch the deflection. But the moment we connect a meter, the original circuit is changed. And now the voltage that we will observe is the voltage which is present in the presence of this meter. Okay, and that voltage may or may not be same as the voltage which was present when the meter was not there. So when we connect a meter, the voltage may change, and we would like that the change is not much. Okay, and that is possible if this meter that we are connecting is not drawing much current from the circuit. If the meter draws some current, then definitely there will be a change in this voltage. Okay, but if the meter is not drawing any current, so that is like these two terminals are almost open, then the voltage that we will get will be almost equal to the voltage that was there when these two terminals were actually open. So we want the meter to draw very small amount of current, and that means the meter resistance should be very high. So we need meter resistance to be very high. Okay, this is the requirement for voltmeters. Now, obvious question that I will ask, how high is high enough? How high will serve my purpose? So, how high is high enough? Should it be 1 kilo ohm or mega ohm, or how much? Again, as we saw in case of a similar question in with ammeters, this answer for voltmeters also depend on the circuit that we are probing, that we are measuring. Okay, so to answer this question, we will use Thevenin's theorem. So any circuit, any linear circuit can have a Thevenin equivalent. So consider the Thevenin equivalent circuit of this circuit, which can be represented as a voltage source in series with a resistance or impedance. These two terminals are the same terminals A and B. Sorry, A and B here. Okay, achha. Now then this resistance, call it RTH, and this voltage, call it VTH. According to Thevenin's theorem, VTH is the open circuit voltage between A and B. That is the voltage we want to measure. Okay, that is what we wanted to measure. And RTH, Thevenin resistance, is the resistance as seen between terminal A and B from outside. Okay, this is open circuit resistance as seen between A and B from outside. Okay, now when we connect a meter, V for voltmeter, with meter resistance, call it RV. Okay, then the voltage that we will measure is the voltage which appears now between A and B in the presence of this meter. So now the voltage that we will measure, we will actually measure is the voltage in presence of this meter, and that is equal to VTH divided by total resistance RTH plus RV. This is the current flowing through the meter multiplied by the meter resistance RV, potential divider rule. So this is the voltage which exists in the presence of meter, and this is what we will measure. And this is of course not equal to the actual voltage that we wanted to measure, that is VTH. So how much is the error? Let us calculate error, percentage error. That will be VTH, actual voltage we wanted to measure, minus the voltage that we are actually measuring, whole divided by the true voltage forgive me for using sometimes little t, capital T, you understand, it is TH for Thevenin. Okay, acha, into 100%, and then VTH will go away. We will have 1 minus this quantity, so that is RTH plus RV minus RV divided by RTH plus RV. Am I correct? RTH plus RV minus RV, yes, I hope. And so this is the percentage error, and we would like this to be small, and so to error to be small, I mean percentage error, this quantity should be small, so RTH by RTH plus RV. Let me divide the numerator and the denominator with RTH, so this will become 1 over 1 plus RV by RTH. This should be small, which implies this quantity should be high. That means RV should be much higher than RTH. So once again, the answer to this question, how high should the voltmeter resistance be, is like this. It should be higher than, much higher than the resistance seen by the voltmeter between the two terminals where we are connecting the voltmeter. So it depends on the circuit we are measuring. Okay, depending on the circuit parameters, if this resistance, if the Thevenin resistance is itself small, few ohms, then even a 100 ohm voltmeter is good enough. But if we are measuring the voltage in an electronic circuit with the Thevenin resistance itself very high, several kilo ohm, then we may need a voltmeter with mega ohm order of resistance. Okay, fine. Acha. Next, okay, we will talk about the voltmeter range of measurement, and range changing, multi-range voltmeters, etc. Range of measurement. Suppose I take a PMMC meter, for example. Okay, some meter PMMC with the specification that full scale deflection current equal to say 10 milliampere, and meter resistance is Rm is say maybe 200 ohm. Okay, so now if we use this meter as it is, then we will get a range of, so this will give a range, full scale range of 200 ohm into 10 milliampere, which means 2000 millivolt, that means 2 volt. What does this mean? I mean, if you apply 2 volt between these two terminals, then how much current will flow? 2 volt divided by 200 ohm, that means 10 milliampere current will flow, and according to the specification of the meter, that will give full deflection. So that means with 2 volt we will get maximum full deflection, and we cannot measure more than 2 volt with this meter as it is. So this is the range of the meter. Now, can we measure more than 2 volt with this meter by doing some modification? Say, can we measure 10 volt using this PMMC meter? That is the question. Can we? What can we do?
By using a series resistance.
Excellent. So suppose we connect a series resistance. Okay. So call it RS, and then this is the meter with Rm equal to 200 ohm. Full scale deflection current is 10 milliampere. Now these two together will be my measuring instrument or the meter as a whole. Now I want to measure 10 volt. I want to see full scale deflection when 10 volt is applied between these two terminals. So I ask, what should be the value of this series resistance? The answer is very simple. So we want 10 volt being applied across these two terminals when we would like to have full scale deflection. That means at that instant we would like to have 10 milliampere current flowing through that, which implies 10 volt divided by 10 milliampere. This is the total resistance Rs plus Rm. This is what we want, and so now this says 10. So how much is this? 10,000 milli by 10 milli is 1000 ohm. This should be equal to Rs plus Rm is 200. So this implies Rs equal to 800 ohm. So if I connect a 800 ohm series resistance, then these two together will make a voltmeter with full scale range of 10 volt. Fine. Now, can we make a multi-range voltmeter? Yes, of course, we will have to use a variable series resistance, and you can do it in many different ways you like. Let this be the meter, and then we can connect multiple resistances R1, R2, R3. This is Rm, and here I have a key switch that can connect to any of these three terminals, and these two are the meter terminals. So this as a whole is my voltmeter, multi-range voltmeter, and I can change the position of the switch, position 1, 2, 3, and accordingly the meter range will change. Now can I ask that if the full scale deflection current is given and meter resistance is given, make a meter which can measure, say, different ranges of voltage, like say here 1 volt, 10 volt, 100 volt. What should be the values of R? Yes? Okay. What should be the values of R1, R2, R3, etc. You can also do it differently. You can do it in many different ways. So now this is my meter as a whole, voltmeter as a whole. These two are the terminals between which you connect the unknown voltage to be measured, and let this be R1, R2, R3. As you change the position of the switch, the actual resistance in series that varies. When the switch is here, only R1 is in series. If the switch is here, R1 and R2 both are in series, and accordingly you can change the series resistance. So this could be different possible schemes for making a multi-range voltmeter, and I will leave this as a homework to calculate how, to figure out how to calculate these resistances R1, R2, R3 for a given choice of different required ranges. Okay, so let that be your homework. By the way, in our course web page, we have a lot of exercise problems, problem sets given for your practice. So practice them. That will help you in a better understanding and having a better grip on the subject. Hopefully. Okay. Fine. Acha. Any question? Okay. Now let us talk about rectifier based ammeters and voltmeters. Okay, so you recall that we once said that PMMC meters are more sensitive than electrodynamic or moving iron. However, that is true particularly for low values of current. PMMC is more sensitive, but the problem is PMMC meter can measure only DC current or DC voltage. Okay, so what we do, we use rectifiers to convert AC into DC, and then use a PMMC meter to measure that voltage or current, so that we get simultaneously more sensitivity as well as we can measure AC quantities. Okay, so PMMC more sensitive, but can measure only DC. With that in mind, let us draw some rectifier based voltmeters and ammeters. So first, voltmeter. Suppose this is a circuit and there are two terminals between which I want to measure the voltage. So I have to connect a meter here. If I connect a PMMC meter, and if this is a AC circuit, if this voltage is purely AC, then sometimes voltage is positive, sometimes negative, current flows in opposite direction. So on an average, the torque acting on the moving coil will be 0, the meter will not give any deflection. What we can do, we can connect say a diode in series. So now what happens, only when this side is positive and this side is negative, current will flow through the meter, and in the opposite half or opposite cycle no current flows. So on an average there is a torque in one particular direction, so we will get a deflection and we can measure this voltage. Now in our course we will assume perfect ideal diodes for simplicity. Although in your textbook they use non-ideal diode with non-zero threshold voltage, I recommend you may simply use ideal diodes for simplicity in this course, but non-ideal diode will be more interesting. However, if you read our textbook about non-ideal diodes, please be careful, there may be some mistakes. So we will assume ideal diodes.
Sir,
Yes.
sir, even if after connecting the diode, maybe it will only measure when it is in the first positive cycle, but still in the first positive cycle, the current will be varying, right? Current will increase and then decrease to 0. So won't it means affect the PMMC, the iron in the PMMC, and affect the measurement, overall measurement?
Yes, that is what I'm going to talk about now. Okay, so so here this voltage V, if I draw the waveform, V is like this. This is V, and the current that flows through the meter I, or would you like this I to be in the opposite direction? Doesn't matter. Okay, so now I, this current will be flowing only in the negative half. Or if you like, I will just change the direction of the diode. If that, I mean, anyway, nothing going to change the things much. But if that helps in your visualization, that's why. So now this is the current waveform. Hello, am I connected?
Yes, sir.
Okay,
Yes, sir.
fine. So this is the current waveform, and now if the current is changing and if we are using a PMMC meter, then the torque is also changing. So current is changing, torque is also changing. So torque is proportional to the current I, and how much will be the average torque? So average torque, average electromagnetic deflecting torque, TD. Okay, this is TD. Let me write it as some K1 times I, some constant times I. So that will be, so average TD will be average value of K1 times I. So K1 times average value of I. How much is the average value of I? If so average value of so this will be K1 times average value of I, and suppose this current I is varying. Before that, suppose this V is varying as V0 sine omega t, and then this current I in the positive half will be V0 sine omega t divided by the resistance of the circuit, total resistance. So there may be also some series resistance, call it Rs, meter resistance is Rm, so Rv, voltmeter resistance is Rs plus Rm. So here I will divide it by Rm. Okay, so here I have to calculate the average of this quantity, which is
It will be RV, right?
yes.
V0 sin omega t by RV.
Oh yes, thank you. Rv, yes. So this will be average value of V0 by Rv sine omega t over only half cycle. Okay. So, and this is constant. You can take it outside. I mean, this is not a precise way of writing it. Let me use some ugly writing. Here I have sine omega t in positive cycle, positive half, and 0 in negative half. So these two together is the current waveform, and you have to calculate the average value of this quantity. How much will that be? Anyone?
1 by pi.
1 by,
The 2 by pi.
no, 1 by pi. 2 by pi is the average of, okay, let me,
So the time interval is like 1 cycle, right?
for this waveform, average value is 2 by pi multiplied by the peak value. For this waveform,
Yes, it will be 1 by pi.
yeah, average is 1 by pi multiplied by the peak value. Now now you will ask here whether I should calculate the average for only this part or this complete cycle, for half cycle or complete cycle. If I calculate for half cycle, average is 1 by pi, 2 by pi, and if I calculate for complete cycle, then it is 1 by pi. which one should I do? What I am trying to find out is the deflection of the meter. For that, I need to know the average torque acting on the meter. Okay, and on which interval should I do the average? I should do the average over over complete interval, because because in this part there will be some torque, in this part there will not be any torque, but the fact that there is no torque in this part will reduce the average torque and will therefore give less deflection. If you do not consider this part, then you will think, oh, I'm supposed to get a higher average, a higher deflection, but you will actually get half deflection, lower deflection, because for half of the time there is no torque. So you should never ignore this zero part. So here this is the average, okay, and now the deflection will, so now deflection theta, okay, we know that under equilibrium spring constant, spring times theta will be equal to the average torque. Okay, so this is like average theta times spring constant is the average deflecting torque, which is this K1 V0 by RV into 1 by pi. Let me write this. So from this I can write theta is equal to K1 by K spring V, then 1 over RV, then V0 by pi. Now this thing is a constant for a meter, and this is the average value, okay, average value of the half wave rectified voltage, average value of half wave rectified voltage. Okay, now let me ask you one question. You have to answer this quickly, okay? Suppose we have a DC calibrated meter, voltmeter. So on this scale everything is marked, already marked in terms of a DC voltage, okay? So and then we will use this in an AC circuit. So this is my DC meter, and I manually add a diode, extra diode, ideal diode, and then the reading of the DC meter comes out to be 5 volt. Meter reading is equal to 5 volt, okay? And now, but I know that this is AC, so I know this voltage V, so we know V is pure sinusoidal AC, okay? And from that, tell me the RMS value of V. This is the question.
Sir, 5 pi by root 2.
Nice. Let us check. So if see, VRMS multiplied by root 2 is the peak value. Okay, now meter reading is, as we saw, that depends on the peak value divided by pi. Okay, so V peak by pi. Now from these two equations you will get VRMS is equal to meter reading multiplied by pi by root 2, which you correctly said 5 pi by root 2. Excellent.
So can't we include pi into the constant? We calibrate the voltmeter in such a way that it only measures V peak, not V peak by pi.
Yes, if you already have, yes, you can do it. Now you take these two things together, and if you can erase the scale and draw a new scale on that, yes, you can do it. But in this question I said that we have a already calibrated decimeter. Okay, yeah, so of course we can now package these two things in one box, in one single box, and then erase the previous marking and write the new markings. Yes, that is what in fact.
So sir, we are saying that it's reading V peak by pi because it is already been DC calibrated. So
yeah, it is because it is already calibrated to measure DC voltage. Yes.
Okay, sir.
Yeah.
Thank you, sir.
Sir, sir, I didn't understand one thing. Sir, in the half wave rectified form which we are measuring, even after first cycle is completed, one has half cycle and another is 0, and then again the voltage will rise. So means theta that you calculated, it's a average, right? It's
Yes.
about one time period average. So will we see that in the meter also? Means will the meter stop at that average value, because the again torque will be produced, and you have not considered any damping, so the pointer may continue to move. So in the meter, what will we see? I didn't understand that thing.
Nice question. Acha, let me try to answer this. Okay. So recall that we wrote the meter dynamics. It was something like this. J, moment of inertia, multiplied by the angular acceleration, okay, plus, so okay, let me write it this way. This is equal to the total force. Total force includes current times some constant. This is the deflecting torque, plus we have, no, not plus, minus spring constant multiplied by theta, and minus damping force K damping. By the way, this is called damping constant. I don't know whether I mentioned the term. That is the damping force per unit angular velocity. Okay, so this is like Newton's law. Inertia times acceleration is the total force. One component from the damping, deflecting, one from spring, one from damping. And from this we wrote J theta double dot plus KD theta dot plus Ks theta equal to Gi. Now, at this moment, recall the system signs that you have learned previously. This describes a system. Theta is the output, I is the input, So this is a system, and if you are considering that this is used as a voltmeter, then this current I could be some voltage divided by some resistance. So this voltage can also be considered as the input. Now suppose this I is time varying. I is time varying. Okay, it could be an AC, for example. It could be a half wave rectified AC or DC, full wave rectified DC. Okay, so all these possibilities are there. And now our question is, what will be the deflection theta? So given I, given waveform of I, find theta. This is the question. Now recall from your previously studied system science, any system can also be thought of as a filter. So systems are also filters. Systems are also filters. Now the question is, what kind of filter is it? So what kind of filter is it? Low pass, high pass, band pass? What do you think? How do we find that? For that, I will tell this briefly. You do thorough calculation at your in your home. Okay. So for that, what do you do? Take Laplace transform, find frequency response. So what do you do? Take Laplace transform and write transfer function. We will get J s square plus ks plus kd s is the Laplace transform plus ks multiplied by theta s equal to g times is, and then theta s will be, or theta s by is transfer function, that will be g over is square plus this is j plus kd s plus spring constant. Now put s equal to j omega to find put this equal to j omega and find the so this will become minus j minus omega square plus, check my calculation, I am doing it in a rush, kd j omega plus ks. Now you put, say, large value of omega. Okay, if omega is large, what will happen to the magnitude of this quantity? For large omega, yes,
It will be
Negative.
it will let me consider the magnitude response. It will be 0, and for 0 omega, for omega equal to 0, you will get g by ks. Okay, so this is a low pass filter. Okay, and now that means what? This if this I is varying with time, that means it has you can do a Fourier analysis, Fourier decomposition of this current, which will have different frequencies, and then accordingly theta will also have different frequency components. However, all high frequency components will die down and only the low frequency part will survive. Okay, and the low frequency gain is this. Okay, so if the current I has a DC component, average component, then that average component will get multiplied by this factor and that will be the average value of theta. On top of that, there may be some oscillations, but average value of theta will be average value of current multiplied by this. Okay, so average theta will be average I current multiplied by G by Ks. In fact, you remember this is actually the sensitivity term. If we go back to our early days where we studied sensitivity, where is it? BAN is the constant G. Okay, that also I wrote somewhere. So BAN by K, K is spring constant. So that is the sensitivity. Sorry, this is 1 over sensitivity. Yeah, it's correct. Yeah, it's correct. More this value, more deflection. This is sensitivity. Okay, what I was telling actually? What was the question? Yeah, the question was, when we have a varying current like this, then what will be the deflection? Okay, and through this analysis, what I want to say that theta will also be a function of time, will be a function of time if I is a function of time. But now average value of theta will be this G by Ks multiplied by average current, average I. On top of that, there may be oscillations depending on the frequency. If the frequency is high, that oscillation will be so small that we cannot observe. Okay, acha. And then this is equal to, I can write in this way, average G times I by Ks, correct? And this is equal, now what is G times I? Is the deflecting torque. So this is average deflecting torque Td by Ks. So what do we see? Average value of theta depends on average torque, average deflecting torque. Okay, so I mean, this is not a, I did it very quickly. So those of you who studied system science before, I believe you can do it thoroughly. Okay, and those some students from a different background may not have done system science before. So no worry, this part is not important for your exam. Okay, but intuitively, average deflection is proportional to average torque.
So sir, means there will be some oscillations, but those oscillations will be imposed on the average component, and what we will see in the meter is the average value of the theta, and
Right.
those oscillations are very negligible, and we won't see, means we won't be able to perceive them.
Right, right. Yes, that is my point. Yes.
But sir, hello.
Yes.
So if the frequency is very less, won't the deflections will be on a larger scale and it won't be focused on the average value? It would be very difficult to read the values.
Yes, 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 absolutely, absolutely. If you are measuring AC quantity with say time period 10 seconds or more, then your pointer will oscillate. And yes, you cannot, I mean, visually it is difficult to measure the average, yeah, not possible. But if you are measuring something of natural AC frequency, our 50 hertz, 60 hertz, etc., then I mean the meters, when somebody makes a meter, they design this coefficient J, G, Ks, Kd in such a way so that I mean these values are so chosen so that at 50 hertz, so frequency response at 50 hertz, this will die down to 0. Okay, so these numbers J, Ks, Kd, I mean you cannot make them arbitrary as you like. They are so designed that for normal frequency 50 hertz or nearby, the oscillation will be, I mean this quantity will be 0 almost. I mean it's very important to design it in that way. Okay, so although we talked about only the sensitivity which depends on G and Ks, and in fact only the ratio, but these things are also important, which we are not focusing much to keep the course simple, but they are really interesting and important. Yes.
Sir?
Hmm.
Sir, I had a doubt in the last class that KCL condition.
Okay. So today's I mean you can now start to drop from the meeting. I will not teach any more new things. Okay, so coming to the studies question. Actually, I mean this was a very interesting question. I was thinking about it today. In fact, at around 10 o'clock, I went to have my bath, and this question was in my mind. When I came out, I found it was 10:50, and I had to rush. So this is really an interesting question, and honestly speaking, I do not have a concrete. I mean, this is the answer, but I can share my thoughts.
So you have said here that the KCL is violated in the case of that inductor and ammeter.
Right.
So, but we apply KCL when the circuit is complete, right? When the switch is closed. So we apply KCL at the time after time greater than 0.
Right.
So at that time u of t is 1. So
Right.
I think it should be I only.
Right. So that is one thing. Also, I thought after yesterday. I mean, I thought later after. So you are absolutely right. So I mean, let me draw both the capacitor case and the inductor case side by side. So I said here, I said KVL is violated, but KVL is not violated after the switch is closed, in a sense. Okay, I mean, very difficult to say in English. What I mean, the moment this is charged
So you
to this,
energy is violated here.
okay, so I will point one thing first. KCL plus KVL, they together implies energy balance. Let me prove it in a minute. Okay, acha. You studied in your previous networks course about what do you call that? What theorem? Television theorem, etc. right? You studied that product of voltage in different branch and current, this is equal to 0. And if you look at the proof of this theorem which you did in the previous semester, so this comes, I mean the proof depends only on KCL and KVL. So any circuit that obeys KCL and KVL must give 0. This is the sum of energy consumed and energy produced. So that total sum should be 0. So if KCL and KVL is not violated at any moment, then energy balance cannot be violated mathematically. Okay, and you are absolutely right. After the switch is closed, KVL is fine. KVL is fine after the capacitor is charged. In the same way, so yesterday I was also talking of a problem that I cannot do it in this way because then before the switch is closed, this current should be 0, which is not allowed. So I later thought of a thought experiment like this. Suppose I have a short circuit here. Okay, this is initially connected, closed. So this current is initially flowing through this switch, short circuit. Okay, and then step number 1, connect this inductor. Step 1. Now what will happen? When you connect this, the voltage across this inductor is 0. So current through the inductor is not required to be increased. So this current will remain 0. Then step 2, open this switch. Now if you open this switch, this current has no other choice than going through the inductor. But now the current will have to increase, and for that definitely a voltage across this inductor is required, and that voltage has to be generated by the source. This source has to somehow generate that voltage. Now this current is changing instantaneously like a step voltage, like a step current. So this voltage will be delta function multiplied by some constant. Okay, now let us do some calculation here. Energy stored in L, that will be of course half L I square finally. But energy, how much is the energy supplied by the source? So for that let us calculate power from source. That will be the product of I into this voltage. I is constant. Initially current was flowing through this short circuit, now through the inductor. So I is constant, but V is a function of time, and V we know is delta t. So this will be I times delta t. Okay, acha, let me put the values. If this is L, then this voltage will be, and suppose I is I, so this, what will be the coefficient here? L di dt. Li, yes. Li delta. Okay, so here I have, let me write here, I one more L I delta T. Now the energy from source, you do the integration. So L I square delta T dt, and this will come out, delta T integration is 1, so it comes out to be Li square. And see, once again, just like this capacitor situation, same imbalance we are getting, Li square and half Li square, just like here. Okay, now how do we justify how do we justify this imbalance? Because we cannot justify imbalance if KCL and KVL are always true. So definitely KCL and KVL is not true, maybe for even a brief moment. Okay, this is actually getting beyond what I actually can do mathematically. So for this case, there is a brief moment. Practically now I'm thinking, there is a brief moment when this voltage is smaller than this voltage. In the same way, here there is a brief moment when this current is actually smaller than this current. Okay, and the remaining current is actually possibly flowing through this short circuit still. And today morning I have shared a research paper, link of a research paper which talks about a similar problem like this capacitor case. And what they say in this case is roughly speaking, the moment when these two voltages are not equal, this is lower than this, then that voltage difference, that is still pushing the electrons or ions, okay, they are still pushing it, but that work done to push the electrons is not lost in any resistance. It is because there is no resistance, so electrons are not colliding with molecules, and that energy is not transferred to the molecular kinetic energy or oscillative energy, anything. But then where is it going? The only possibility is it is increasing the kinetic energy or speed of the electrons. That is one way. Of course, there is another consideration which I am not going into, is that we cannot even have a closed loop, closed circuit without inductance. So this, whenever we are saying there is a closed circuit, definitely there is some inductance. Why? Because I have a closed loop, and the moment current flows, it will generate flux, it will cause some flux linkage. So that inductance we are also not talking about. And if you have studied some electromagnetism, then when you have inductance, capacitance, they will create oscillating voltage, current, and electromagnetic waves, and with that waves also some energy can get lost. All those things come into picture, and it is beyond my mathematical skill, so that I can model everything and show you, yeah, see, this is the case. That's beyond that concrete thing I cannot do, but these are the things which are coming into my mind, that okay, there will be definitely some inductance. And also in this case, one very interesting thing you observe, like here there is an inductance which we are ignoring, here there is a capacitance which we are ignoring. Where is that capacitance coming from? See, for a brief moment, even for a brief moment, we need a voltage to appear across this inductor. Otherwise current cannot increase. So we need voltage. But how can we get voltage? Voltage can come only if there are some charges or accumulation of charges. So definitely for a brief moment there will be an accumulation of positive charge here and negative charge here. You can think in this way that the moment you open this this thing, I mean this switch, then current is not able to go through this switch. So the current I will definitely go in this direction. So I amount of current is going in this direction, but here current cannot increase suddenly. It will take some time. So here less amount of current is going. So what is happening? I mean I is coming here, here I have less current I. So the remaining current must store some charge here. I mean so here we are getting some accumulation of charge and here negative charge. And that accumulation, that positive charge and then this negative charge will create a potential difference from top to bottom, which will cause the required voltage to increase the current. Now one thing we can do, this is what we can do, this is within our capabilities. Now model this thing as a parallel capacitance. Okay, because you see we are getting an accumulation of charge, because we are having more current here and less is passing, so we are getting accumulation of charge, and that accumulation of charge can be modeled using a capacitor. Now maybe that capacitance is very small, very negligible, okay, so that's why we are ignoring, but definitely there is some capacitance. Now if you do this math you can do, then what you will see is this. You will see the average current. So this you can do, I mean write the differential equations, okay, and find the current through this. You will find the average current through the inductor is I, is a step function, but on top of that there will be oscillations. And if I model this capacitance, this C to be small, when C is small, we know the oscillation frequency will depend on 1 over root over LC. If C is negligible, then this frequency will be very high. That means on top of an average current I, there will be very infinitely high frequency superimposed, which we cannot perceive. And that is one way of possibly explaining this. But now if you say what happens if this C capacitance is really 0, once again that is going beyond my mathematical skill. I mean, so these are really interesting things. These are not important for our exams, but I mean yesterday when these questions arised, and I don't know whether whether I'm giving the right clues. Once I thought maybe I should delete these parts from the published videos, but then I thought this is the part that I am enjoying most, and this is the part which will keep reminding possibly all of us that this is the part which I really do not understand well. So it will keep me stimulating for a thought behind this. So this is really interesting and really interesting, that's what I can say. If you are interested, I mean, then this mathematics that I told very briefly, someday I will take maybe half an hour and do it thoroughly.
So means still means according to yesterday's class that we discussed, means theoretically it is not possible to connect a plain capacitance with a means directly to a voltage source, right? Because
Yes.
it will violate. Theoretically it's not, means we can't do that.
Yeah, because then I don't know how to how to do the mathematics consistently.
Yes, sir. And in practical situations, whatever we connect, there has to be some resistance in the
Yes.
wire. So practically it won't be a problem, I think.
Practically there is no problem. In fact, you assume there is a R, do all the calculation, and then let limit R tending to 0. No problem. Because the energy loss in the resistance in calculation does not depend on the value of r. So even if you let r tending to 0, small r, and no problem, still we have energy balance. So practically, I mean, in an engineering class, one suggestion could be assume non-zero resistances here, etc., and then go to the limit r tending to 0, or in this case, r tending to infinity. Then everything is fine.